All right, welcome back to part 2 of week 13, Tuesday's lecture, for those of you following along with Northwestern's Physics 1 class, now online. All right, so we're moving along in chapter 7, which is all about extended systems, which includes internal energies, and now we're going to be talking about energy transfers due to temperature differences. So last time we talked about how to calculate delta E thermal, and now we're going to talk about something called heat. So the plot's going to thicken a little bit. Okay, so we already know that work is a mechanical energy transfer into or out of a system. And it takes place macroscopically. All right, so what we have already talked about temperature, where we've got these series of atoms that are vibrating around, and the speed of their vibration is related to their temperatures. That is clearly not a macroscopic system. So we need to go back to our subatomic way of thinking about matter and interactions. All right, so for heat, think atomic. All right, so let's say we've got our two blocks again. We've got a block here. It has a high temperature, and then we have a block here, and it has a low temperature. Now, we know that the temperature flow is going to go from hot to cold. Now, we get to chapter 12, we're going to talk about why that is, but for now, that's your experience. If you put ice cubes in a glass of warm water, the ice cubes will melt as the heat from the warm water will flow into the ice cube. So this is our energy transfer. Okay, and this energy transfer has a name. We call it Q. No, I didn't get to name any of these things. They came with these names when I started the field of physics. And I think now with my chosen profession to teach at a small college, I will probably never get to name anything cool. That's okay, though. I get to teach all of you. You're more fun when I can see you, though. All right, so this essentially describes the atoms doing microscopic work on each other. So Q is subatomic work between the atoms. I know, physics is so poetic. I love it. All right, so eventually all the atomic springs will be vibrating at about the same amount. So in this case, we know that they're going to reach equilibrium, and in that case, the atomic springs vibrating at the same rate. Same-ish rate. So to really go after this, we need to do a little bit more thermodynamics and statistical mechanics, which is a way awesome field to study. So it is something to look forward to. All right, so let's write out a couple of definitions. So Q is energy transfer due to temperature difference. Q can be positive or negative. It's sometimes called microscopic work. All right, so we can now use this knowledge to update our energy equation. So, because as I told you, basically from now until the next couple of chapters, we're just going to be taking that energy principle and fleshing it out and fleshing it out and fleshing it out and having a deeper and deeper understanding of just, I mean, how cool of a tool it is. All right, so the change in energy of a system is equal to Q plus work. So temperature transfer and then any macroscopic work. So in our previous problems that we've been working on, there simply was no temperature transfer that we were including. So now that we know this expression, we can now solve problems where that doesn't need to be neglected or where it's actually, happening. And this is true for something called an open system. And yes, we do have a nice discussion of open and closed systems coming up. So in other words, not isolated. Okay, so let's talk. We know Q can be positive or negative. So let's talk about the sign of Q, because I saw the sign. I opened up my eyes and saw the sign of Q. It can be positive or negative. So for those of you that like 90s music, you're welcome. All right, so if energy transfer is out of a system, either you're appreciating these or you're worried about my sanity. Out of a system, Q is negative. For example, so hot, less hot. This is our system. And the energy transfer is going out of the systems. That is a minus Q, and that would of course mean this is the surroundings. All right, so once again, we're seeing system choice matters. All right, so if energy is transferred, into a system, Q is positive. So in this case, we could say this one is our system. It is less hot. This is the surroundings, and it's getting some energy. So then we would have a nice positive Q. So if you're receiving energy from heat transfer, then it's positive. If you're giving it away, it is negative. All right, so I need to introduce a standard convention for how we think about the universe. And yes, there are philosophical implications for this. This is something you can explore in your paper. You will see this topic explored in your various readings. So for the universe as a whole, and there are physical implications. So this is something that is even debated within the physics community, depending on who you talk to. Q and W are 0. Energy does not change. And the universe is closed. So essentially, this is what allows us to have the energy principle, because if the universe was not closed and some external force could do work on it, could do an energy transfer on it, then you wouldn't have the same energy that always is and always was and forever will be. Now, like I said before, you will occasionally read documents that will question the strength of the statement right now. That is mostly a question that is had in philosophical circles, although I have known of people who have asked about the theoretical implications of this. So I've not read about multiverse philosophical implications extensively, but this would be a potential convention. But for now, in this classroom, I want you to think deep philosophical thoughts. Think about these things, write papers on these things, but then use the standard conventions for doing physics, which is that the universe is closed. So just because you're using a standard convention doesn't mean you can't question it. Question everything. Be skeptical. All right, so more standard conventions. We need to get to the physics meaning of heat, because we use heat colloquially. Man, that is a hard word for me to say. And it means something different than in physics. So heat in physics refers to an energy transfer across a system boundary. That is heat. That is what we mean in physics by heat. Now, it doesn't mean that scientists are just as capable of using colloquial terms as much as anybody else, but if you are looking at heat in a physics problem or paper or book, this better be what they're referring to. Okay, so building on this concept, there are other kinds of energy transfers. And again, this is just fleshing out our whole idea of the energy principle. So we know about work, which is an energy transfer. So mechanical work, which is F dot dr. So for example, throw a ball, do work on the ball, changing the kinetic energy. Q, energy transfer due to temperature. Temperature difference, so boil water, and you'll introduce some Q. You can have a matter transfer. So for example, you could fill a pool with water. That's going to change things and transfer around some energy. You could have a mechanical wave. So let's see if I can do this with this spring here. So we've got a mechanical wave, poorly done. And sound is actually an example of a mechanical wave. So right now, as I'm speaking, I am compressing the air molecules around me, and you are hearing the effects of those vibrations. All right, and then we also have electromagnetic radiation. Which we'll talk more about at the end of Physics 2, and an example of that is sunlight. So all of these are different types of energy transfers that can happen. It's not an inclusive list, but these are the main ones that you're going to see. Okay, so let's update our energy principle again. Now that we know more things that we might need to try and account for. So all we're doing, we're not really devising anything new. We're just expanding and fleshing out what we know. So the change in energy of a system is equal to contributions from work plus Q, that thermal, that temperature difference, energy transfer, plus any other transfers. Okay, so right now we're going to go through kind of a lot of concepts, and that's how we'll finish out chapter 7, although there are quite a few, there's still some more problems to do. Okay, so I need to introduce something called the steady state. The steady state is not equilibrium. They're two different concepts. So a steady state system, the energy does not change. Even though there are transfers into and out of the system. So at the turn of the last century, prior to the Big Bang Theory, the predominant theory of the universe is that it was a steady state system. So there were transfers of energy into and out of it, maintaining a steady state. So whatever you had coming in, you also had it coming out. So the Big Bang threw the steady state universe theory on its head because a steady state universe could be infinitely existing. The Big Bang shows that the universe has a beginning. So it's not a steady state, it's constantly changing. All right, so let's do an example of a steady state. So you have an electric heater and it gets an input of 7,500 joules of electric energy from the outlet. So during this time, the heating element is maintained at a constant high temperature. What is delta E thermal? For the heater. And what is Q? The energy transfer from the heater to the heated cooler air. All right, so our system is the heater. Our surroundings, the electric wires, and the air. So it's receiving energy from the electric wires and it's giving energy out to the air. So we need the energy principle. So the change in energy of the system is equal to the work plus Q plus anything else going on. Okay, so fleshing that out, leave that right here so you can see it. Delta E system is equal to work plus Q plus electric would be the other. 0 is equal to 0, no work from the surroundings, plus Q plus 7,500 joules. So Q is equal to minus 7,500 joules. What comes in must go out. All of this is still just an application of the energy principle. So, and this is an example of a steady state. So, so if the heater was insulated, no energy could flow. So, and the reason we knew delta E system, we talked about it was just a constant high temperature. So it was maintaining the same energy the entire time. And if we insulated the heater out, so basically you've got a box, you've got your heater here. So now what's going to happen is, this is the room out here. The room's going to stay cold. The heat's just going to keep getting hotter and hotter because we still have that energy coming in from the electricity. And basically what's going to happen is the heat, or the temperature, sorry, see, I'm susceptible to it too. The temperature would increase until the heater melted. And it breaks. So you don't always want a closed, isolated system. In this case, the steady state system that was open was the ideal system for the heater. Okay, so you might be asking, is Q the same as delta E thermal? And the answer to that is no. Two different things. Delta E thermal is the change of thermal energy. And Q is the energy transfer. Due to temperature differences. These are two different concepts. Do not use them interchangeably. All right, so in the previous example, delta E thermal was equal to 0 because it was maintaining a constant temperature. But Q was equal to minus 7,500 joules. So it was getting Q, but maintaining the same 0 change in thermal energy. All right, so that wraps up part 2 of Tuesday's lecture. I will see you for Wednesday's lecture where we will continue on with chapter 7.